So we have been studying the lithosphere, and you guys have been learning about different landforms in deserts, landforms created by glaciers, and you've also been reading about landforms in the coastal zone. So this lecture is going to actually focus on a couple of aspects of coastal terrain, and they are coastal erosion and sea level change. You have also learned that there are many types of coastal landforms, from beaches to marine terraces and everything in between. And how these landforms are created is influenced both by the plate tectonic setting of the coastline, as well as the past and current ocean conditions, things like waves and currents, which are the main agents that sculpt coastlines around the world. So as we focus in on what factors influence coastal erosion, we might also be interested as to why certain coastlines seem to erode more rapidly than others, or some coastlines are very resistant over long periods of time to erosion. So we're going to focus in on about 7 specific factors that influence coastal erosion, and they are degree of wave exposure, tidal range, rock composition, the presence or perhaps absence of coastal protection structures, if a coastline happens to be in an emergent or submergent kind of tectonic setting, and things like climate events and sea level change. So with respect to degree of wave exposure, take a look at this feature here. First of all, can you name the coastal landform? And hopefully you have already identified this as a tombolo, which of course is some kind of offshore rock feature. The waves come in to shore, and because this prominent rock is protecting the waters behind it, sediment can settle out. And so we get this forming a strip of sand that connects the offshore rock to the mainland, which is the definition essentially of a tombolo. So here we're looking at waves coming in, and as they're hitting the rock, this area here is actually getting a lot of wave exposure. It's getting really pounded by the waves. But notice in the regions behind the rock, all of this sediment is settling out, and we can actually even see further beyond some boats that are harbored in there. So these are quiet, protected waters in here. So not a whole lot of wave exposure in where those sailboats are moored, but definitely a lot of wave exposure out here. Tidal range. Well, tidal range, of course, is the high water height at high tide minus the water height at low tide. So in other words, how much vertical change is there over the course of, say, a day, or average that out over a year or several years, and you get a look at how much the water level goes up and down on any given tidal cycle. In general, places that have very small ranges in their daily tidal cycle means that the water level, where the waves are hitting a coastline, say a cliff, that energy is going to be concentrated in a smaller vertical area. Whereas if you have a very large tidal range, that wave energy is going to be distributed over a much greater area throughout any given day. And this picture down here on the lower right is from Cornwall, England. And I want you to just notice how these boats are moored. It's probably close to low tide in this shot. So we can see that there are steps that go all the way down to the boats. But sometimes when the tide's in, the boats are right up at the level of the dock. So this is one of the locations in the world that has a very large tidal range. Here on the west coast of the U.S., say California coastline, our tidal range is somewhere on average about 8 feet maximum per month, meaning that most of the time the water height and therefore the wave energy is concentrated over a small region. The largest tidal range of anywhere in the world is in Nova Scotia, Canada, the Bay of Fundy, which has a maximum tidal range of 65 feet. So what about rock composition? What material the cliff is actually made of? And I want to combine this with the presence or absence of what we call coastal protection structures. And coastal protection structures are things, engineering kinds of things that we humans put in to protect a coastline from eroding, from wave attack. So oftentimes in a place where the rock composition is very soft, you're going to see people have built more coastal protection structures because those coastlines erode more easily. In places like that previous picture of the Tombolo, you've got this very resistant granitic rock out there. It's very strong and it's very resistant to wave erosion. And so you don't need to emplace a coastal protection structure there. So this shot here, and I want to actually tell you guys a story right now. It's a really interesting story. Comes from the southern Monterey Bay. This shot was taken in 1972 from the air, from an airplane. And it shows a red-roofed building over there kind of on the left. And that building is known as Stillwell Hall. It was the officers' club at the former Fort Ord military base, which is now the California State University Monterey Bay campus. So the cliffs in this area of the southern Monterey Bay are essentially made of sand. I mean, they're really sand dunes that are quite ancient sand dunes. They've been vegetated. The sand is very stabilized by the vegetation, so it's not moving around like an active dune. But the Pacific Ocean hits these ancient, or what we call paleo dunes, and because of the composition of that material being just sand, it's very easily eroded. So the Officers Club was built on these cliffs, on these paleo dune cliffs, overlooking the Monterey Bay. Beautiful spot for a club, a social club. It was not built up at the edge of the cliff as we see it here in 1972. It was built some distance back from the cliff edge, but these, because of the rock composition, or the composition of the sediments of this cliff line, are so soft, the coastline began to erode and retreat quite rapidly. So by 1987, looking at this view now, again from the air of the Officers Club at Fort Ord, we can see some materials have been emplaced along the base of the cliff, probably some rock material, rock rubble, which we call riprap. There is also a little seawall, a concrete seawall at the base of the cliff, kind of on the beach itself. And then there's some kind of gray material coming down from the platform surrounding the Officers Club all the way down to that rock rubble at the base of the cliff. So because, again, of this soft rock composition, probably the military in this case decided to try and protect this building. They could see what was going to happen. They built the building 100 feet back from the cliff. 20, 30 years later, it's already up to the edge of the platform surrounding the building. Another 20 years, and it's getting undermined. So they put in some different coastal protection structures here to try and save this building. By 2002, let's take a look at it again. So things are not looking good. This is actually starting to turn into almost like a peninsula. So we can see that right in front of the Officers Club, where all the coastal protection structures have been emplaced, it is stabilizing the cliff. But to the left and to the right of those protection structures, notice how the cliff line continues to retreat back. In other words, it erodes back. But there's still a big sandy beach in front of the area on the left and a sandy beach on the area to the right of these coastal protection structures. Is there a beach in front of the coastal protection structures? No, there is no beach. So this, by the way, is an example of what we call passive erosion. It means that in areas where you allow the ocean to kind of do its natural work, which is to erode coastlines, the beach is a feature that gets maintained. It doesn't go away. But when we try and halt the erosion process, And we can do that effectively depending on the kinds of engineering structures we build and the kinds of materials we use in those structures. But we lose that beach. By stopping the erosion, we actually lose the feature of the beach. And I always like to ask the question, who owns the beach? Who does the beach belong to? And in different parts of the world, you'll get different answers. In fact, in different parts of the United States, you'll get different answers. But in California, the beach is a public resource. And part of our state legislature has been to establish the California Coastal Commission. And one of their primary their primary goals is to maintain public access to beaches. But I've digressed a little bit. I want to bring us back now to Stillwell Hall and to this story here of looking at how this particular region is eroding and how the coastal protection structures are either being effective or not in this case. So 2002, here we are. We can see that some of the protection structures are failing, and now we see exposed cliff material, which is again the ancient sand dunes. And the building at this point has been abandoned. This is no longer a military base. It's now been given over to the state university system. So people were deciding, what are we going to do? What's going to be the fate of this building? It looks to me like in 2002 from this picture, it's going in the ocean, right? It's hanging over the edge of the cliff. And to think that we can hold back the Pacific Ocean, the largest ocean on our planet, the third of the Earth's surface, with a pile of rocks is, pretty optimistic, but foolishly so. So what do you do? What would you do? Okay, so 2004, we could see there's no building, right? It's gone. The other thing that you might notice that is missing is all that rock rubble. All of the coastal engineering structures that were there to protect the building have been removed because, again, the California Coastal Commission requires that those materials be removed. And do you notice something else that's starting to come back in the absence of these protection structures? The beach. So you can start to see that the beach is coming back because now this part of the coast is being allowed to erode naturally. And so things are going to kind of smooth out over time, and the beach, the public beach, will re-emerge. Another factor that can influence the erosion of a place is the plate tectonic setting of that coastline. And in places where we have an active plate boundary, such as the west coast of the United States, the tectonic activity is actually causing the coastline to emerge or uplift out of the ocean floor. So many of the cliff rocks, the coastline of the west coast, are made of marine sedimentary rocks that were formed on the ocean floor and have been pushed up by tectonic activity, by tectonic processes, and are now exposed to the waves. So one thing we might ask is, if this cliff is, or this coastline is coming up, is it eroding? And yes, it is very actively eroding. And this is mainly due to the fact that once rock material, be it sedimentary rocks or harder rocks, get exposed to that surf zone as they're pushed up by the tectonic forces, the waves are going to attack, and they're going to start to try to round things and smooth things out. So in this shot here, which is really a shore platform, we can see this flat rocky platform, and then this sort of softer material of a cliff that has grass growing at the top of it. This material is eroding, very, very actively eroding. So even though the coastline's being pushed up, you have very active erosion. And some recent studies of erosion rates along the California coastline showed that 86% of the California coast is actively eroding. Just want to show you guys a couple of other shots here of emergent kinds of landforms that we find along the west coast, along an active plate tectonic coastline. And this comes from Santa Cruz County right here, some sea cliffs. And we can see just these very vertical cliffs. And there's all kinds of erosional features in these emerging rocks. One more example, this is kind of getting towards San Francisco, Pacifica, California. And these are very, very steep vertical cliffs. We can see there's a lot of erosion. They're soft, young sedimentary material, and there's a whole lot of houses built up there at the top. How do you create such a steep vertical cliff? Again, it's the plate tectonic setting, and that sets it up for very, very active erosion, because as soon as that material emerges above sea level, the waves want to attack it. So what about the opposite tectonic setting at a passive plate boundary, such as we find along the U.S. East and Gulf coastlines? What's going on there? Well, these areas, because they're not tectonically active, and also due to the fact that there's a lot of large river systems that are delivering enormous volumes of sediment to the coastline, to the shoreline every year, there's a lot of material, sedimentary material, that's weighing down on the lithosphere and actually causing that coastline to sort of submerge or sink down under the weight of all that material. So in this shot from the Gulf of Mexico, we can see the Mississippi River Delta. So these plumes of sediment in the Gulf waters here are coming mainly from the Mississippi. There's also the Atchafalaya River, and all of that brownish, murky water contains particles of rock, eroded, transported, weathered rock that eventually will settle onto the seafloor and will cause the whole coastal area to sink down and submerge. So some of the features that we find in this region where there's an abundance of sediment are things like sand bars and sand spits and barrier islands, all along the east and Gulf coasts of the United States. Now, do these features erode? Oh, they definitely do erode. So you get erosion both on emergent and submergent coasts, but because of the fact that there's so much sediment here along the East Coast and Gulf coasts of the U.S., what happens is things kind of get rearranged a lot. The barrier islands get shifted. The sand doesn't actually disappear, but it just gets into a different orientation. And of course, if you happen to have buildings and roads built on these barrier islands, they too will get shifted. So here's an image from, this is one of the barrier islands in North Carolina. This comes from a study by the U.S. Geological Survey. And so what we see here now is a short-term climatic event like a hurricane, and how that influences both sea level for a short period of time and obviously erosion. And we can see many of these homes were devastated, destroyed, knocked into the ocean by these kinds of events. So what about long-term climate change and global sea level change? So I want to make sure that you are familiar with this term eustatic, E-U-S-T-A-T-I-C. Eustatic just is a fancy way of saying global sea level change, eustatic sea level change. So here we have the eustatic sea level curve, and you've seen this graph before because we've talked about the change in oxygen isotopes that correlate with temperature. So this graph here is also correlated to sea level changes over geologic time. So on the upper graph here, we can see that sea level has gone up and down and up and down and up and down over Earth history. The lower graph focuses in on the last, say, 36,000 years of Earth history. And if we look at that red curve, going back to the right now, in this case, back in time is to the right on this graph, 36,000 years ago, sea level was pretty close to where it is today. And then about 18,000 years ago, it dropped because, of course, that was the time of the last glacial maximum, meaning the Earth was covered in a lot of ice. And so sea level naturally drops if that ice is not melting and water is not flowing back into the oceans. Since 18,000 years ago, Earth's temperature has changed, Glaciers have melted, global ice is diminishing, and as it melts, that water is flowing into the oceans. And we can see that rise in sea level for the last 18,000 years has been about 120 meters, over 300 feet of sea level rise just in 18,000 years. Pretty amazing, right? So what does this do to coastlines? How will, in fact, global sea level change as it continues to rise, as Earth temperature, as we predict, will continue to warm? How are these coastlines and coastal erosion and the kinds of landforms that we find going to be influenced by this? So let's look at this gorgeous image of, can you tell where this is? You guys should know this. This is the San Francisco Bay, which of course is a tectonic estuary. Beautiful, beautiful shot here of the Golden Gate. We can see all the sediment coming out of the rivers into the San Francisco Bay. Okay, so think about what is happening tectonically in this area. First of all, we know we have tectonic uplift, right, going on along the west coast of the United States, but because of the particular setting here where the San Andreas Fault is literally running right through the center of the San Francisco Bay. It runs, northwest, southeast, just like the orientation of the bay. Some of the areas in the bay itself are actually dropping down. They're subsiding with earthquake events. So we have both uplift and subsidence going on here. So how might global sea level rise, you overlay that on top of the tectonic setting, what might be some predictions of how things are going to look in, say, a couple hundred years in the San Francisco Bay? So let's also look at this sea level measurements, actual direct measurements from a tidal station in the San Francisco Bay for, say, the last 100 years or so. So we actually have tidal data going back to 1900 from the San Francisco Bay. And that blue line here, that up and down blue line, are actual measurements by people, okay, of sea level. What we can see is that over time, the trend of the line is going up. So that's that red line that's been drawn in there, that best fit line. And that is global sea level rise. So that's just happening. It's happening around the world. But what is really interesting about this graph is that sea level doesn't just go up with the line. There are peaks and there are drops, and there are some really dramatic spikes in sea level, in local sea level, just in the San Francisco Bay. We see one in 1915-16. We see another spike in 1940-41. We see another spike in 1957-58, another spike in 82-83, another spike in 97-98. And all of these spikes are associated with an El Nino event. So really the take-home point here for us all to really be thinking about is that we have global sea level rise going on everywhere, okay? It's eustatic, happening worldwide. But we also have climatic events that occur on top of that. It could be a hurricane. It could be an El Nino event. It could be a storm surge associated with a tsunami event, okay? Some kind of tsunami wave. So the factors influencing any particular portion of a coastline around the world can't be distilled down to one or two factors. There are many that need to be considered. So I start with that list at the beginning for you. And I actually want to encourage you to think about what other things could be added to that list. And I think that's all for now. Thanks. Bye.